Okay, so get ready because today we're going to be like totally bending our minds, right? We're diving into geometry.
And not the boring kind from high school.
Right. This is like next level geometry. We're talking about like questioning everything, shapes, lines, even what a point is.
Exactly. We're starting with a question that might seem deceptively simple. What is a point, really? I mean, we're taught to think of it as this zero-dimensional thing, just a location on a plane, no size, no real existence.
Right, like the tip of a pin, but infinitely smaller. It's kind of an abstract concept when you actually think about it.
Exactly. And this is where our deep dive starts today. We've got excerpts from this text, pasted text, and just throws down a gauntlet right in the preface, like straight up says, Euclidean geometry. We've hit a wall with that.
A dead end, they called it. So I'm already hooked. Like, tell me more. Why is the traditional way of doing geometry a dead end?
Well, the author argues that starting with these abstract zero-dimensional points, it's too limiting. You're trying to build a whole universe out of, well, nothing.
Okay, I'm starting to see where this is going. So if points aren't these zero-dimensional things, what are they? What's the alternative?
This is where it gets really wild. The text proposes something called CPS Geometry, stands for Closed Packed Singularity Geometry. It's based on the idea that points, instead of being those invisible dots, are actually tiny spheres.
Tiny spheres. Okay, now my mind is officially blown. Spheres. Why spheres?
Because think about it. Nature loves spheres. Atoms packed together in these close packed structures. Look at how, like, oranges fit perfectly in a crate. Spheres just, they fit together so elegantly and efficiently.
So instead of these abstract points, we're starting with something that's already like a thing. It has form.
Exactly. And the source even points out this fascinating fact. Did you know that a sphere can be perfectly surrounded by exactly 12 other identical spheres?
Okay, now I'm trying to picture that in my head and whoa, it's a lot. 12 spheres all touching perfectly.
Right. And that interlocking potential, that's key to understanding why certain structures in nature are so stable, so efficient.
Okay, I can see that. But how does starting with spheres instead of points, how does that fix the problems that Euclid ran into? I mean, you said a dead end earlier.
Right. And the text calls it out pretty directly. Traditional geometry, it can't quite explain certain things, especially at really small scales or really large scales.
Yeah.
But when you start with spheres, with their inherent curvature, the way they pack together, it offers this whole new way to model those really complex spaces.
So are we saying Euclid was just wrong this whole time?
Not necessarily wrong, more like he gave us a set of tools. And those tools work great for a lot of things. But like any tools, they have their limits. What's exciting about CPS geometry is that it's like discovering a whole new toolbox, one that might be better suited to tackling these mysteries that Euclidean geometry just can't quite grasp.
I'm starting to get why this is kind of a big deal. It's not just about swapping shapes, it's a whole different way to understand space itself.
Exactly. And this shift in perspective, it could change everything. I mean, this has huge implications for fields like physics, cosmology, even computer graphics.
Okay, now I'm really intrigued. So, like, let's get into it. What are some of these big implications?
Well, there's this quote from the text that really caught my eye. It talks about the philosopher Leibniz and his thing for the equilateral triangle.
Oh, yeah, because it treats all points equally. That stood out to me too. But what does that have to do with spheres in CPS geometry?
It leads to a fascinating question, right? If we redefine a point as this tiny sphere, does that change how we think about equality, about symmetry within geometry itself? Does it give us a different way to understand how points relate to each other? It's these kinds of questions that this whole new perspective opens up.
It's like we're taking this idea of a point, which is so abstract, and making it into something you can almost like hold in your hand, those tiny spheres. It just feels so much more real than just talking about location and no size.
Exactly. And that shift from abstract to concrete, it's huge because it changes how we understand everything we build on top of that idea of a point. Lines, curves, dimensions, even space itself. It's like,
How can I explain it?
okay, so I'm a visual learner. Got any good analogies? Help me wrap my head around this.
Analogies. Love them. Okay, imagine you're building with Legos.
Now you're speaking my language. I can work with this.
So traditional Euclidean geometry, it's like you're working with just those individual Lego studs. You can build amazing things, don't get me wrong, but you're starting with the most basic unit. It's very abstract. Right, like each time you build something new, you're starting over with just those single points.
Exactly. But now imagine someone gives you pre-made units, right? Like little sphere connections, where the spheres are already part of the building blocks. You still have freedom, you can still create, but there's this inherent connection built in from the very start. That's kind of what CPS geometry is doing, giving us a different set of building blocks for understanding space itself.
So it's not that one is right and the other is wrong. It's more like they're different approaches, each with its own strengths and weaknesses.
Exactly. And like any good crassus person, scientist, whatever, you want more tools in your toolbox, right?
Yeah.
Multiple perspectives, because each one can reveal something new. And this brings us to something really interesting that the text touches on, something called Riemann's hypothesis.
Oh, yeah. That's one of the biggest unsolved problems in mathematics. I remember hearing about that. What's the connection to all this geometry stuff?
Well, Riemann's hypothesis has to do with prime numbers, right? Those building blocks of all other whole numbers. And what we're talking about here is essentially, are we looking at the fundamental building blocks of geometry in the right way? If our very idea of a point is up for debate, who's to say that it couldn't influence how we understand other fundamental concepts in math, like prime numbers?
Whoa, okay. So you're saying that by changing how we visualize a point, we might find new ways of understanding prime numbers too? That's a pretty wild connection.
It is wild. And the text doesn't get into the specific equations or anything like that, but it does highlight something really important. Our assumptions shape how we see the universe. If something as basic as the definition of a point might be wrong, what other foundational elements of science might we need to take a second look at?
It's almost a scary thought, right? Like, what if we've been building on shaky ground this whole time?
It's not about being scared. It's about being open to new possibilities. This whole exploration into CPS geometry, it's a good reminder that even our most basic assumptions deserve to be questioned from time to time.
So instead of clinging to the old ways of doing things, we should be excited about exploring new perspectives, even if they seem strange at first.
Exactly. Who knows what amazing discoveries are waiting for us when we dare to question the very fabric of what we think we know about the universe.
It's like, you know that saying, if you always do what you've always done, you'll always get what you've always gotten. Like, maybe to find new answers, we need to try new approaches.
Totally. And what I think is so cool about pasted text, this whole thing we've been looking at, is it doesn't try to say CPS geometry is the only answer. It's more about like opening up to the idea that there could be other ways of describing the universe, other ways that work just as well.
Which gets you thinking, right? What other facts in science might not be as solid as we think they are? Like, are there other connections we're missing because we're so used to seeing things in one specific way?
And that's what I love about this kind of exploration. It's not just about memorizing new things, it's about getting that sense of wonder back.
Yeah. It's like how kids see the world, always asking why. Somewhere along the way, we lose some of that. This deep dive is making me want to be more like a kid again.
I love that, and it makes me think about how scientific progress often happens. It's when someone asks a different question, looks at something familiar from a new angle.
So we've gone from thinking about points as tiny spheres to like questioning the entire basis of geometry. Now I'm thinking about all kinds of big questions. This deep dive has been quite a ride.
And hopefully our listeners feel the same way. It's just the beginning, right?
Totally. So next time you see something round like a basketball, the moon, even just a drop of water, take a second to really look at it. It might be a tiny clue to understanding the universe in a whole new way.
Or at least it could be the start of an amazing conversation.
That's what we love about these deep dives. Thanks for joining us as we explored the wild world of CPS geometry. Until next time, keep those minds open and keep asking those big questions.